Ya, Assalamualaikum warahmatullahi wabarakatuh and good day. Let's continue our session 2 auto cycle for part 4. This part is also we will try to solve example in auto cycle. Okay, let's read example 2.2. An ideal spark ignition engine has a compression ratio of 7. The temperature and pressure at the beginning of the compression is 50 degrees Celsius and 1.02 bar respectively. The cycle maximum temperature is 2000 degrees Celsius. So determine the mean effective pressure of the cycle. So now let's read it carefully. Let's read it carefully, okay? An ideal spark ignition engine. An ideal spark ignition engine, it means that auto cycle is not necessarily the problem in the questions they use auto cycle. They can use another word such as spark ignition engine to show to replace the word of auto cycle. So the ideal spark ignition engine or auto cycle has a compression ratio of 7. So they give you RV equals 7. The temperature and pressure at the beginning of the compression is 50 degrees Celsius and 1.02 bar respectively. So what is mean by the beginning of the compression? So what is the mean of the beginning of compression? It is actually easier if we could recall the PV diagram of auto cycle. In this PV diagram of the auto cycle, we can see that P is for pressure, V is for volume of specific volume. So at the beginning of the compression process, so we know that when the volume decrease, which means that the compression occur. Okay, the compression process occur. So which means that from 1 to 2, okay, from state 1 to state 2, the volume is decreased. So the compression process occur at 1 to 2. When it say the beginning of course, which means at the state 1. So temperature and pressure here is actually temperature at 1 and pressure at pressure 1. Okay. And then we continue again. We continue to read and to understand the example. It says that the maximum temperature is 2000 degrees Celsius. The maximum temperature is 2000 degrees Celsius. So, again, if we can recall the PV diagram, normally we are not giving you a PV diagram, okay? So you have to recall by yourself, you have to remember by yourself. So PV, when we recall back, when we look to the PV diagram, we know that the highest pressure is at 3. Okay, and we can see that the heat addition process occur at 2 to 3, which means that the combustion process occur from 2 to 3. And after the combustion process, N is the highest pressure. So when the pressure is high, temperature also high, and therefore the maximum temperature stated here is actually T3. So with this, okay, now let's try to solve example 2.4. But at first, it is important that if we can try to sketch the PV diagram of the autocycle, the PV diagram, so that we can see it clearly. Okay. This is actually a straight line, okay? This is a straight line. Okay, now the process occur at 1 and 2 and 3 and 4. At 4 to 1 is the heat rejection process. 2 to 3, of course, is a heat addition process. 1 to 2 and 3 to 4 is isentropic process. So actually, it is easier. We can see here that volume V4 is actually equal V1 and V3 is equal V2. This is important. And then it is easier. No, it is easier. It is actually if we can write, if you can jot down, yeah, the formula for all processes that it actually is very easy because Q in and Q out using a similar equation, which is CV T4 minus T1. But for heat addition, Q in, we just change this one into 3 minus T2. Okay? But actually they are using the same equation. And for equation 1 to 2, 3 to 4 is isentropic process. So again, they are using the same equation, that is P1 over P2 V2 over V1, yeah, power of K, which is also equal to T1 over T2 power of K over K minus 1. Okay, for process 1 to 2 is P1 over P2, but process 3 to 4, you can change this to 3 P4, 2 to 4, this one is 4, this one is for 3, 1 also can be used for T3, and T2 also can be used for T4. So it's really simple, all right? So now after we know we have sketched and know all the formulas that can be used throughout the process. Now we're back to the questions. That the question need us to determine the MEP. What is MEP? Is actually we're net over Vmax minus Vmin. Okay, Vmax is actually at 1 and Vmin is actually at 2. Okay, but you can also change. You can also rewrite again this equation. Actually, we can rewrite again by rewrite again by changing by divide it all to kg, so we can have all in kg in specific volume, something like that, to work net. This is work done per unit kg. Okay, so specific volume at 1 over R V. Okay, so normally we will use this equation, yeah, the substitute one, and we name it as equation 1. Okay, next let me see what we have, what has been given by the questions. Okay, given by the questions. So what is given by the question? Okay, what is given by question is given is RV 7 is 7. Okay, RV is actually V1 over V2, and then we have T1, temperature at 1, 50 plus 273. Change it change it to all to Kelvin. Okay, temperature must be all in Kelvin, pressure must be all in kilopascal. Okay, and temperature at maximum. Okay, and then what else? A constant that we have, K is 1.4, CV is 0.718 kilojoule per kilogram Kelvin. Okay, we already know that this constant we already give you or show you at session 1. Okay, session 1. And then what else we have? We have constant air to 7 kilojoule per kilogram Kelvin. Okay, so this is what all the things that we have, the data that we given by the by the from the example. Now let we start to solve the problem. Okay, I'm gonna change the color. Okay, now we try to solve. We know that we need work net. Okay, we know that we need our work net. So work net is Q in minus Q out. So Q in is CV T in T3 minus T2. Now we have been given from the questions T3. Okay, we have T3, we have CV, but we don't have T2. Okay, we don't have T2. So how can we get T2? It's actually by using isentropic equation. So isentropic equation from that one. We can have T2 T1 over T2 K minus 1 equal V2 minus V1. Okay, now let me see that forget about K. Okay, V2 over V1 is similar to the this term is actually 1 over RV. Okay, so you can substitute 1 over RV in this equation, and then T1 is given, so that we can find the T2. Okay, we can find T2. Okay, now we already can find T2. So when we already can find T2, so we can get the value T2 from this equation. Okay, can get value of T2 from this equation by substituting the answer from this equation. Then we can get Q in. Okay, now let's solve for Q out. Q out. Okay, let we solve for Q out. Q out is actually CV T4 minus T1. Okay, so now we have T1 is given, CV already know is constant, but we don't know about T4. Okay, we don't know about T4. So again, we are using the isentropic formula from T4 to from state number 3 to state number 4. Again, we use this equation. Okay, T3 over T4 power of K minus 1 is equal to V4 over V3 K. Okay, K. So now T3, we already know T3 given. We want to find T4. K we already know. And then V4 over V3 is actually V4 is actually equal to the V1. And V3 is actually equal to the V2. So this one is actually R. So it's actually compression ratio R. So you just substitute the value of R given to this equation, then you will get the temperature. Okay, you will get the temperature and try to solve for Q out. And now we already have calculate the work net. So work net is done. Okay, done. Now, what is the value for specific volume? Specific volume at 1 and RV is 7. Given, okay, given. So RV is compression ratio is 7. So now we have to find only V1 specific volume at 1 to solve this problem. Okay, now how can we get this specific volume for V1 is actually from ideal gas equation. That's why we have to make an assumption that ideal Otto cycle, we have to use the air standard assumption. Remember? Air standard assumption. So we will assume that all the working fluid is gas, an ideal gas. So we can use ideal gas PV equal MRT. Okay, we can use PV equal MRT. Okay, now you know that we already know that P V volume over M is RT, which this one is actually a specific volume. Yeah, specific volume. So the unit will be meter cubic over kg. Yeah. Okay. So that's why by solving this equation, we can have V1. Okay, I will rewrite it again. So what is the pressure temperature that we have for both? We have both pressure and temperature at state number what? Can you answer that? If we look to the what data has been given to us, we only know the pressure and temperature at 1. So that's why we are using data at state number 1. R is constant, okay? So T1, okay? So can see here we have P1 is we can see here P1 is 102 kilopascal. V1 is the one that we want to solve, we want to find, okay? R is a gas constant, air gas constant, and then T1 is given. So obviously we can find specific volume, and then we substitute the answer to the equation number 1, and then we can determine mean effective pressure for this example. Okay, can you get it? Okay, now you can see the answer at the bottom of the slide. Okay, you can try by yourself, try to calculate by yourself, so that you will know which parts you understand and which part you will feel like confused and you need to ask your lecturer. Okay, so it is the end of the example 2.2 solution.